field direction, and magnetization will have a maximum value. So this is the saturation value. So this 100 and corresponding that family of directions. Okay, when I say that, I mean what I mean by is 1 bar 0 0 0 1 0 0 1 bar 0 0 0 1 0 0 1 bar. So these 6 directions. Which why am I getting 6 directions? Because it has a cubic anisotropy. So in the cubic anisotropy, x, y, z directions are all equal 90 degrees angle, and a is equal to b is equal to c, alpha is equal to beta is equal to gamma is equal to 90 degrees. So everything is isomorphic. In that sense, they are like, there's no difference between those 3 directions. And when I say one direction, and opposite to that also is the same. So there are 6 directions. And these directions which are phase diagonals, which are represented by 110 family again. Okay, so there are again a number of, depending on those 6 phases, you will have corresponding directions. Okay, so 110 family, we call this as intermediate, because neither it is easy nor it is hard to saturate the magnetization. And you see that the magnetization, of course, you see this is basically the value of magnetization that you get. Okay, it's of the order of 1600, 1700 Gauss is the saturation magnetization. Okay, for iron. So this number is also important. I don't need to remember anything, but I'm just asking you. Look at this number, right? For intermediate case, you see that the magnetization will slowly raise beyond this field. And then eventually, of course, it saturates. Okay, that's around 400 Oersted or so. And along the hard axis, you see the magnetic field has to do more work. So you need to apply more and more field in order to bring align the movements along its direction, which is 111 body this is body diagonal direction. The magnetization eventually saturates. So this, as I told you, that is related to the crystalline orientation, and this is a typical experimental graph, and people can actually do calculations, and then also you can also see that this is an agreement with the theory also. And for example, nickel, which is also a cubic system, but it has a face-centered cubic system, and in this you see it is opposite, exactly opposite. That 111 body diagonal is the easy axis of magnetization, and you see the field again is actually much smaller in comparison to this, but the magnetization that you can get, the maximum magnetization that you can get is also smaller. It's only around 500 Gauss. Okay, and 110 in both the cases is an intermediate, and qubit is the hard axis of magnetization for nickel. And when it comes to cobalt, which I showed you yesterday, hexagonal closed pack structure. So in this you have like a c-axis and a basal plane. So the basal plane, basal plane is like this is the c-axis, so parallel to c-axis I'm plotting. So the magnetization, you see, it rises fast for almost like very, very small field. This is what yesterday somebody was asking. You have an internal field. Yes, there is a strong internal field. That is why the magnetization rises so fast. Okay, but why we need to apply the field, that I will discuss today. But you need to apply. You need to define some quantization axis or some direction along which you are measuring. Okay, so that is the role of the field here. And eventually, with increase in the field, see the field again. You see this is like order of magnitude more. This is like 2,000, 4,000, 6,000, 8,000 Gauss like here. So eventually around 3,000, around 1,500 Gauss or so, it gets saturated and then remains so. And the maximum magnetization that you can get is around 1,400 Gauss. Whereas perpendicular to c-axis, that is in the basal plane, you see it's very, very difficult to saturate. Even a field of the order of 8,000 Oersted is not able to saturate. Okay, so you have to really apply much more, more field in order to saturate this. So this is this. So what you see is that the energy that is associated with this magnetocrystalline anisotropy will be minimum when the spins orient along the field direction, and this will be maximum when the spins orient perpendicular to the or along the hard axis. Okay, so this is one energy which we discussed yesterday. Then I also want to give some data on magnetic data on these ferromagnets, elemental ferromagnets. Okay, for example, iron, which is an elemental ferromagnet, has a magnetization 1,707 CGS units. This is Gauss. This is what I was showing you here. Okay, this is like 1,700 Gauss. this gets 290. Of course, this is temperature dependent, you know. So it 1700, and for cobalt you see it is around 1400, and for nickel you see this is like, you know, 485, close to 500, and for gadolinium it is around 1090. And this is a saturation value. This is a magnetization at that value, and saturation is M0. That means at 0 Kelvin. At 0 Kelvin, there is no temperature, thermal energy to randomize the spins, and intrinsically the moments are all oriented along the particular direction, and that's the maximum magnetization that a material can have, which is called saturation magnetization. And you see that this value is, you know, these numbers, and this is the effective spins per unit atom. Okay, suppose for each iron atom, in terms of Bohr magnetons. Bohr magneton is the magnetic moment associated with one unpaired electron. So for iron, you have a magnetic moment of 2.2 Bohr magnetons per iron atom. And similarly for cobalt, it is 1.7. For nickel, it is 0.6. And for gadolinium, it is 7.1. Does anyone has any question here? If you are intelligent and smart,
Yes, sir.
you should ask a question here. Yeah.
Yes, sir. Sir, how is the saturation magnetization value is greater than the magnetizations?
Definitely, right? Saturation is the maximum magnetization that the system can have. So that is why it is the greater.
Even if oh, okay, I thought it's spontaneous magnetization.
No.
Oh, I
See,
thought it.
this is also spontaneous. At 0 Kelvin, both are equal, right? But
Okay,
otherwise, I
okay,
cannot
okay.
measure at any temperature. These numbers are actually okay, spontaneous, but then spontaneous, remember, is the temperature dependence, and it goes to 0 at Tc, right? And it will have a maximum value at 0 Kelvin, which is equal to the saturation magnetization. Okay.
Okay.
So that is why these values, when I measure it, something like 290 is close to room temperature. That's what I'm trying to show here. At room temperature, these are the values. These values are less than this naturally, right?
Yeah, okay.
Okay, yeah.
But okay.
Yeah. I was expecting another question. Can anybody, something does bother you? Something which is very strange?
Why nickel has less than 1 Bohr magneton?
Okay. That is depends on what? What determines magnetic moment of the element? From where you are getting magnetic moment?
So magnetic moment develops from the charge and the orbit angular momentum associated with it. So basically, the orbital angular momentum as well as the spin angular momentum contributes to the magnetic moment.
Spin angular momentum is a major contribution. Okay, orbital will also be there, but spin angular momentum is a major contribution. So that, what decides that?
The spin of
that means how many unpaired electrons are there.
Yes.
For example, for gadolinium, you have 7 unpaired electrons. Okay, and each unpaired electron will contribute to 1 Bohr magneton magnetic. Okay.
Yes.
That's why for gadolinium you have something like 7 Bohr magnetons. Okay. So I'm asking. I'm waiting for another question. And nickel, see, for the same reason, the other student, I cannot see who is over this question, but nickel has a less magnetic moment, tells you that number of unpaired electrons per nickel atom are less in comparison to other fellows.
Okay.
But can anyone ask any other intelligent question? Interesting question. What did I say? What is the magnetic moment? I mean, see, these are in terms of Bohr magnetons. Again, please remember, like, you know, for iron it is 2.2 Bohr magnetons, for cobalt it is 1.7 Bohr magnetons, for nickel it is 0.6, and for gadolinium it is 7.1. And what is 1 Bohr magneton? Yes. That's the magnetic moment associated with one electron, one unpaired electron. Okay. Yeah. So I'll wait for you guys to go back and think about it and tell me what is the question that I was expecting from you. So I'll not tell. I'll not tell out. Okay. Look at another interesting parameter here. This is the TC. Okay. I put TF for some other reason. Don't worry. Don't worry. This is basically the transition temperature above which the material becomes paramagnetic. And you see for iron, the TC is 1043 Kelvin. Okay. And for cobalt, you see the TC is 1400 Kelvin. Nickel, it is 630. And gadolinium, it is 289, which is close to room temperature. This again, I will talk about this later. And dysprosium, that's another element which is ferromagnetic, has a TC of around 105 Kelvin. Okay. So these are the TCs that we have, and all this data, this one and the previous view graphs, I have taken from this book, Physical Principles of Magnetism by Morris. Okay. Yeah. So this basically tells you that what is the magnetization of these elemental ferromagnets, what is the effective magnetic moments, and what are the TCs. And that means up to what temperature these materials will show ferromagnetic properties. Okay. So then I go to the next point. So as I told you, we discussed two energies so far. One is the exchange interaction, which basically tells you that the spins have to be parallel to have minimum energy. We are discussing ferromagnetism, so don't worry about being anti-parallel. So J is positive. So exchange will be minimum if the spins are parallel. That is what it determines. And which direction, it doesn't care. But when it comes to the other energy that we just now discussed, is magnetocrystalline anisotropy. According to this, if the spins are parallel to the easy axis, then the energy is minimum. That means, for example, again, I just want to introduce a term here. These two fellows, what is that? Yeah, these two fellows have cubic anisotropy. That is why there are different directions in which the spins can orient. That means there are multiple, multiple directions in which the spins can orient, and the energy is the same for all along 100 family. But for C, it is only one axis. So that is why this is called uniaxial. So you remember, C axis is the parallel, like the spins are parallel to C axis, energy is minimum. So the anisotropy, this kind of anisotropy is called uniaxial anisotropy. Whereas in this case, it is called cubic anisotropy. Okay, because the structure is cubic and it determines the energy minimum if the spins are oriented along those directions. Okay. So then now I'm going to introduce another important energy, which we call as a surface or shape energy. So what does it mean? What it means is, suppose you consider some sort of ellipsoid sample, okay, and then it can either you can apply an external magnetic field, or even in the absence of external magnetic field, because of the coupling between the spins, that is a Heisenberg exchange interaction. If the spins are all pointing along this direction, let us say, okay, if the spins are pointing along this direction, then what happens is, we know that we will normally I am associating this arrowhead with the north and the tail with the south pole. Okay, like because conventionally we have been used to bar magnets. So same thing, we can each elemental magnet I can call it as a bar magnet. Okay, or the magnetic moment associated with the spin can be analogous to a bar magnet. I can always visualize. In that sense, the arrow head points north pole and the tail points south pole. So you see that these field lines will actually come and close like this. So inside the specimen, if you look at it, the field lines will be opposite to the externally applied magnetic field, which basically determines the magnetization throughout the sample. But you see, because of these induced poles, okay, because when you say this is the field direction, what it means is that you have actually this is how the sample is getting magnetized. But because of these induced poles, you have field lines which are opposite to the externally applied or internal magnetic field that is present in the system. So this, if you look at it, if I call this as the effective field, which is nothing but the external field minus this field, because the spin system will now see a field which is an algebraic sum, okay, taking sign into account. This is the field seen by the spin system. So just because this field is opposite to the external field, and what is the role of external field? External field is trying to magnetize the spin sample by orienting the spins along this direction. Whereas this internal field, I mean this surface spins or these induced poles will are in the direction opposite. So I call this as a demagnetizing field. Okay, because it is trying to reduce the effect of external field, or it is trying to reduce the total magnetization in the system. So this is called demagnetizing field, and the demagnetizing field is proportional to the magnetization itself. Okay, because if the magnetization is more, the induced poles are more. If the magnetization is less, the induced poles are less. Of course, there is a proportionality constant which is given by the shape factor, which I call as n, which is called demagnetizing shape factor. I'll come to that in a minute. So, if you consider a paramagnetic material, intrinsically the magnetization is small. Someone has a question? Okay. Intrinsically, the magnetization is small, so the demagnetizing field is also small. So there is not be much of a correction. Like Hi is almost equal to external field. But this is not true when you consider a ferromagnetic sample. In a ferromagnetic sample, since the magnetization is large, the demagnetizing field also will be large, and it is decided by the shape factor. For example, if you consider a very long cylinder, okay, if I consider a long cylinder and I apply the magnetic field along the axis of the cylinder, then what happens is, you see, like, your simple Coulomb interaction kind of a thing. These now, because in the long cylinder, what happens is the length to diameter, the diameter is so small in comparison to the length, and so the number of induced pole density will be small, and they are separated at a larger distance, so that the effective energy or effective demagnetizing field is negligibly small. So in fact, for all practical purposes, I can call this as n as 0. Okay, so if it is a long cylinder, I am magnetizing the specimen along the axis. But in the other hand, if I am magnetizing along perpendicular to that, then what is happening is, now you see that more and more specimens, induced poles will be there. So for example, if you take L to D ratio as 1, then the demagnetizing factor can be 0.27. And if there is a sphere, if you consider a sphere which has a larger, the surface area will be there, and because of that, the induced poles can be all around. So the demagnetizing field also can be very large. In fact, there is a calculation. I will show that how shape will decide and how to calculate that. That notes, because I'm not calculating anything in this class. It's only giving you some concepts of magnetism. But I will, to supplement what I'm talking about, I'll upload a document which tells you how to calculate the demagnetization factor. Okay, for a sphere, it can be as large as 0.33. So this shape factor is this is also called magnetostatic energy. Why? Because it arises due to the induced poles on the surface. Okay, so this, what do you expect is, yes, question?
Sir, I had a question.
Yes.
Sir, you complete this topic, then I'll ask.
Okay, take it. So then, okay, there is also another energy which is called anisotropic energy. I'll come back to that a little later. So what is happening now? See, actually, this so-called magnetostatic energy is very, important, and it is responsible for the spin system to break into domains. Okay, see, if you look at this sample to start with, let us consider that the bulk of the sample, if you consider it as a single domain. What I mean by single domain is that all the spins are all oriented along one direction, which is represented by this big arrow. So let us say that this is since all the spins are parallel, your exchange energy is minimum. So there is no problem. System can remain stable because the exchange energy is minimum. The first condition which we discussed. And let us say that this is the easy axis of magnetization. Suppose, okay, if it is a uniaxial system, let us say like a cobalt, like a hexagonal rose pattern structure, and let us say this is parallel to C axis. In that case, this can be the easy axis of magnetization. So the energy will still be minimum. But you see that if the whole sample is a single domain, then what you have is you have induced poles, which are actually, these are like, all the north poles will be here and all the south poles will be here. And because of that, there is a large demagnetizing field, because the density of these surface poles is larger So there will be a sizable demagnetizing field. And this energy will also get added to the total energy, which I will show in a minute. So system will try to reduce this energy if possible. Okay, so the game is to go to a minimum energy configuration. In fact, I will go to the next slide and show. So the total energy, total magnetic energy, we are only talking about magnetic energy, that decides the spin orientation. Okay, the spin orientation or the net magnetization is a sum of, this expression is in the absence of magnetic field. If it is a present, magnetic field is present, then I have to of course write Zeeman energy also. So I am not considering, I am considering about intrinsically what happens to the system when I do not apply any magnetic field. So then these are the energy terms that I should be worrying about. I mean, that I should take care. One is the exchange energy. So exchange energy, what it does, it basically tells you that the spins have to be parallel. Yes, spins are parallel in this case, no problem. Okay, and the second energy which I am referring as anisotropic energy. This is called EK, is the anisotropic energy. Anisotropic energy demands that spins have to be parallel along the easy axis of magnetization. So if I say that in my expression that this is the easy axis of magnetization, then I don't worry. Okay, so this would be the easy axis of magnetization, and then the energy can be minimum. Then the third term comes is magnetostatic energy, or also called demagnetizing energy. I will not discuss this for a minute. I will come back to this later. This is called a magnetoelastic energy, that I will discuss later. First, we'll consider these three energy terms. So having obtained exchange and anisotropic energy minimum values, my focus would be to minimize this energy. You understand? So how can I minimize this energy? So that is what I'm trying to do. So suppose if the same sample, if I can break into two domains, let us say this view graph you look into. Okay, so I'm saying that there are two domains, and what are these domains? In each domain, the spins are parallel. So as far as exchange energy is concerned, within a domain, the spins are all parallel. So no problem. It is not increasing. Exchange energy, at least within the domain, is not increasing. Okay. Of course, when I consider the whole sample, I have to add that, but I'll come back to that. So let us say that if I'm considering a single domain, the spins are all parallel. So there is no additional cost involved in dividing this into two domains. Okay, because in this domain also spins are all parallel, in this domain also spins are parallel. Okay, I did not tell you what is happening in between. We'll come back to that later. Then within this domain, the spins are all still pointing along the easy axis of magnetization. Okay, so the second energy EK, also is not changing because that is in the minimum energy configuration. And so is the case in this domain also, because when I say uniaxial, I've been telling you uniaxial, when I say along plus Z and minus Z, the energy is the same. Energy, it really doesn't distinguish whether the spins are pointing along minus Z or plus Z. So that way, if all the spins are pointing along this direction or this direction, EK also remains the same. Then what happens to the magnetostatic energy? You see, the moment I divide into two domains, you see that by our convention, which I discussed earlier, the arrowhead points north poles and the tail points the south poles. So for this domain, you see, the situation is the same. You have north poles and you have south poles here, right? But then when you come to the second domain, you see that you have south poles here and north poles here, induced poles. So what is the advantage? The advantage is now the field lines can get close. I mean, they can close here itself. So you can actually from north to south, the field lines are closing, and so is here. So north to north, south. So field lines are getting closer. So they don't need to have such a large, demagnetizing field. This field I told you, right? These induced poles are creating a demagnetizing field. So that kind of a situation is not there now. So the moment you break this fellow into two domains, you see that the magnetostatic energy is reducing quite a bit. So as per our expression, the total energy will get minimized if I break this fellow into two domains. Okay? And I am extending this argument to another point, I'm saying that, okay, why should I stop with 2 domains? Why not I break this fellow into 4 domains? So I say that, okay, I am breaking now into 4 domains. I have one domain in which the spins are pointing up, another domain spins are pointing down, and the third domain spins are pointing up, and the fourth domain spins are pointing down. So now I have these induced poles, north, south, and similarly here, south, north, north. And you see that the induced pole density as well as the distance between them, so that the field lines can close much easily in comparison to even this situation. So the associated magnetostatic energy will further reduce. So I will have an advantage if there are no, if I break this fellow into further domains. Then I say, okay, can I have a situation where I can reduce the magnetostatic energy to 0? Yes, when can I do that? I can do that if there are no induced poles. Suppose I have a situation such that there are no induced poles, then the magnetostatic energy is 0. So then what happens is I have to worry only about these 2 terms. So I wanted to explore that possibility. Luckily, if you remember iron, okay, you have cubic anisotropy. Cubic anisotropy will allow you to point spins along these directions also. Let us say this is like, along C, then this is B, even B direction spins can forward. So suppose if I have a configuration in which there is a domain in this way, and then there is another domain in this way, there is another domain in this way, there is another domain in this way, so that this is called a closure domain. So the field lines are completely closed as described by your Maxwell equations, but at the same time there are no induced poles, thereby there is no magnetostatic energy. So in this configuration, the magnetostatic energy is 0, so that is the minimum energy configuration. Okay, so if, this is like a cartoons, but I have to argue out, and I also have to tell you what happens in between and all, but I'll take a couple of questions here.
Yes, sir. Sir, could you go back to the slide where you started with the discussion of demagnetizing field energy? Yes, sir. Sir, this demagnetizing field which you talked about, that induced dipoles are being generated when an external magnetizing field is applied. This
Okay,
is viewed.
I have to correct you. It can arise either because of the externally applied field or because of the internal field itself.
Okay.
Because the sample is magnetized intrinsically because of the internal field. And I am assuming a situation where it is magnetized such that it is a single domain. Okay, if it is a single domain, then the induced poles will be there, which will create, which actually what is the role of internal field? Internal field is doing the same thing as the external field, the same analogy. Okay, but because I have not introduced you domains, I am comfortable assuming that, okay, there is a single domain, and I am saying that, okay, the spins are all oriented because of the exchange interaction, and that like an external field, so you don't need to apply actually external field. Okay, intrinsically, ferromagnetic sample below this temperature, below 1043, any temperature, it can be room temperature, it can be 400 Kelvin, it can be 500 Kelvin, it will have some magnetization. May not be a maximum like, which is at 0 Kelvin, but you will have some magnetization. For example, at 300, it has still sizable magnetization, isn't it? So this magnetization is enough to create an internal field which will orient the spins along a particular direction, and then you will have induced poles.
Okay, sir. Initially, when you started with discussing magnetism, you said that when external magnetizing field is applied, there will be induced dipoles, which will be in the opposite direction. Induced dipoles generated inside the magnet, let it be any kind of a magnetic material, in the opposite direction to the external magnetizing field. So is that magnetization safe? Is that thing similar to this?
No, okay, you are getting confused. Okay, that induced movement I was talking about is for arising because of the completely paired electrons, okay, which do not have any permanent magnetic moment. I am talking about induced movements which are present in all materials, and that is coming because of the completely paired electron. So don't get confused. I'm not talking about that at all. Okay, now, and that magnitude is much smaller, so they are negligible in ferromagnets at all. You don't even see the signature. Okay, even in
Okay,
paramagnet,
okay.
it's negligibly small. The moment I told you also when I introduced paramagnetism, the moment you have a one unpaired electron, the magnetic moment associated with that will be slow high that you don't see any effect of diamagnetism. Okay, in fact, 3 orders of
Okay.
magnitude more. So I am not talking about that. These induced poles, please, okay, you say surface induced poles, let me put it this way. So these are surface poles which are arising because of the shape. Okay, what you have is, let us say, okay, you have, like, north pole and you have south pole. If you can see my hand, I'm so sorry, but if you put a sample here, suppose there is a north pole here, there are south poles which are induced here, right, on this fellow, and similarly this is the south pole, there are north poles which are induced here. So in the inside, from north to south, the field lines will be there. Outside, you see that external field would be in this direction, which will magnetize the specimen. But because of the surface poles, as I plotted here, as I showed you here, see, this is the inside, which is dictated by the external field. I am only talking about the surface poles, which are, now you see that these field lines will be opposite to that, because these field lines will be from north to south. Do you understand that?
Yes, sir. Yes.
Yeah. So
Actually, sir,
I'm
uh,
talking about these surface poles. So don't get confused with the diamagnetic induced poles, which are coming because of the paired electrons.
But sir, diamagnetic, those induced poles will be for every material, no? Not
Every
only
material is,
necessary diamagnetic. Means
yeah.
other cases it will be less, but it won't be like zero.
Yeah. So we don't actually see, this is a induced EMF because of the Faraday's laws. Okay, there is a change in
Yes, yes.
magnetic flux when there is a magnetic, but that
Yes,
will be
yes.
present when there is, when you change the magnetic field. So here I'm talking about, you don't need to even apply external field. Okay, intrinsically,
Okay.
just because of the competition, just because of the coupling between the spins, you see that there are magnetization. There is also induced force. So
actually,
I'm not saying there is no dB by dt.
sir,
Okay.
sir,
Yes. Someone else.
there is, sir, there is too much background noise.
Why is that? Everybody has muted except me. All of you, please mute. Hello.
Yes, sir.
Yeah. Only fan is on. I'll switch it off if it helps. Is it better now?
Yes, sir. It's
Yeah.
fine.
Okay. So, yeah, is this point clear now?
Yes, sir. Yes.
Yeah. Okay. Any other question? Anyone else wants
Sir,
to ask
the,
this point?
sir, one more thing before you come to that wise molecular field theory. The Sir, my question was that you said even if you don't apply an external magnetic field, there will be an internal magnetization which will create a magnetic field itself.
Yes. 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 Yes.
So, uh, and that magnetic field is also responsible for creating dipoles inside that surface dipoles which you are talking about.
Correct. Correct.
Okay, and in case of closure domains, which you said, there will be this whatever magnet induced dipoles, the surface dipoles, they will get nullified.
There
Is
will
it
be
so?
no induced pulse, because there are no field lines going out of the sample. They are all, inside closed.
Okay,
They are getting closed. So there is no surface pulse at all.
okay, okay, okay,
Any other
okay,
question?
sir. Sir,
Anyone else?
so
Actually, only one student or two students are involved. I'm not happy with this. How many are actually there online? 43 students are present. So I don't see that. Yeah. You asked.
so it that magnetic field due to internal magnetization will get added up with the when external magnetic field is applied.
Yeah, with the negative sign, because you see that. Okay. You are right. 1 second. Let me see. I'll go back to this. This expression you are talking about. See, when external field plus internal field together. Okay, internal field because of the molecular field. If you have to put it that. Yes. Okay.
Okay, sir. Okay,
Yeah.
sir. That
Yeah.
was, I just wanted to clarify. Okay,
Yes.
continue, sir.
Any other question?
Sir, we are talking about magnetic energy. What is it is actually Magnetic
Huh?
energy. What is magnetic energy?
Magnetic energy is okay. See, the magnetic energy, when I say, it's like, Zeeman energy. When I say, what is the Zeeman energy? Minus mu dot B. That is, in this expression, you mean to say this expression?
Yes, sir.
Yeah. So, okay, the total energy of the magnetic system, which arises because of different contributions, which will essentially determine the spin orientation. So that is what I'm talking about. That is what I'm calling it as a magnetic energy, because I'm not putting any KBT term or anything in terms of other energy, chemical energy, binding energy. All that I'm not talking about. That is all given. When I'm looking at a system, let us say some system I'm considering. This system is made up of some material which has certain bonds and a certain energy. Okay, there may be some potential energy, there may be some chemical energy, and there may be some thermal energy because it is at this temperature. So all those things are, which also should be added to this total energy, but none of them are relevant as far as the magnetic spin is concerned. Okay, thermal energy is relevant, but if I keep the temperature constant, then I am not worried about how the temperature is affecting. So what I am talking about is, given the entire other energies are all constant, what determines the spin orientation in a ferromagnetic material, to be specific? Then I say that is what I am calling as magnetic energy, which is precisely determined by the exchange energy, the anisotropic energy, the magnetostatic energy, and another term, magnetoelastic energy, which I'll introduce to you later. Does it answer your question?
Yes, sir. Sorry, I have asked the wrong question. What is, sir, magnetostatic energy?
Magnetostatic energy is nothing but your demagnetizing energy. It is basically the surface. It is the energy associated with the induced poles. And if the number of induced poles, okay, as I told you, in this case, the magnetostatic energy is large because there are more. There are more poles, and at the same time, the poles are well separated, so the energy associated with that would be very large. Here you see that since the moment you break into the domains, the magnetostatic energy will reduce quite a bit. Okay, I am showing with cartoons, but those of you who are interested, I will give you calculations also. Okay.
Sir, in last diagram, magnetic
Yeah.
field outside the material is zero, but inside it is.
Inside, no, what you have is basically, you have a closure domains. So for example, okay, I'll ask you something else. You have seen electromagnets? Remember seeing electromagnets anytime?
Yes, sir.
I think I may have picture yesterday's picture. Okay, actually this is not a good picture. Okay, you see here, can I zoom it? No, right? 1 second. 1 second, I will actually try to zoom this picture. You see this? Okay. Hello.
Yes, sir. Yes,
Okay.
sir.
So you see, these are pole pieces, right? These blue ones are pole pieces. Okay. And these pole pieces, if you remember, they have to be anchored, right? You have to hold them. So you are holding against these fellows, right? But then if you look carefully, the whole thing is, these fellows are arrested in a rectangular structure. Do you see that?
Yes, sir.
Yes, sir. And then you have coils inside these pole pieces, and there is a power supply which will energize these coils, so that you get a magnetic field between these pole pieces. Okay, actually, you see, they are shaped into this so that the maximum magnetic field is there, and the sample is kept here. This is nothing but a vibrating sample magnetometer, but this is true for any magnetic system. You go to any magnet, not just a magnetometer. You see, if it is an electromagnet, I'm not talking about superconducting magnets. Okay, that are different. But in electromagnet, you see that this is the kind of system. You go to MRI machine, you go to any place, you see that this is do you know why this kind of rectangular structure is required?
No, sir, I don't.
Why can't we just fix it like that without this kind of a rectangular strip? Because the field lines have to close, isn't it? And the field lines, you do not want the field lines to come out. If you do not have this rectangular field strain, which is made up of iron, iron has a high permeability. So it will ensure that the field lines are actually completely enclosed within this structure itself. If this is not there, the field lines will emanate out, and then you will get so-called a stray field outside the electromagnet. And if I apply a strong field of the order of 2 Tesla or more, then outside also you will have a large field. So any and every material in that room which consists of iron, that will be pulled into the electromagnets. So they basically, you go and bombard between the 4 pieces. Do you understand that what is happening? Okay.
Yes, sir, I understand. But the question is,
now I will come back to that question. So how this is happening? This is happening like, that the field lines are completely enclosed within this rectangular strip, so that there is no field outside. Okay. So similarly, I will come back to this picture now. What you have is, if there is a possibility, this is not possible in all the materials. There is specific materials only. For example, in a hexagonal closed structure, like in a which has only one axis in which the spins can orient, that is the C axis, either C, parallel to C, or opposite to C. So in that, this would be a hard axis of magnetization. So if I put this kind of a orientation, immediately the anisotropic energy will increase. So I cannot do that. Do you understand? So this kind of a configuration is possible only when you have more than one axis. For example, in iron, which has a cubic anisotropy, in which the spins can be either along C axis or along B axis or along A axis, in that configuration, energy is the same. So you can still have this kind of a configuration, which will leave that the field lines are completely closed inside without leaving any surface poles.
but sir, it contain energy. If the field is present, then there is some energy.
Yeah, no, field is present and energy is there. I'm not saying that. What I'm saying is these field lines which are arising because of this surface poles. There are no surface poles here. Okay, this is basically completely enclosed within that. The magnetic poles are completely inside the specimen, so there are no surface poles. So there is no magnetostatic energy. I'm not saying that there's no magnetic energy. There is a magnetic energy. I mean, there is of course exchange energy. There is also anisotropic energy, but that is constant. I'm not changing that. Those values are the same.
Yes, got it.
Okay, but all of you missed it. I thought you people will ask me. You want? I'll give another option. In the previous this one also, I expected one question. By looking at these numbers, I thought you people will ask some question, which I'll wait for the next class. Next week, you have 1 week time to think about it. And here I'm expecting one question.
Sir, why don't the paramagnetic materials also, they will also have unpaired electrons, right? Why
Yes.
don't they
Why don't they?
form domains like ferromagnetic?
No. So there is no coupling. They don't talk to each other. So what dictates? Why they have to first and foremost requirement is that there should be a coupling between the spins to orient along a particular direction, because domain is the region in which the spins are all parallel to each other. And that mechanism is not there in paramagnets. Even though they have permanent magnetic moments, they don't talk to each other. They talk to each other only through field. So when I apply a field, the field will try to align the spins along its direction. Okay, that is how you get a magnetization. But otherwise, if the field is not there, then they are all randomly oriented at any given temperature, thereby giving the net magnetization 0. So there is no question of concept of domain there. To have domain, you need to have interaction between the spins. That's the primary requirement. What holds the spins together? That's the interaction. Okay, so that is what is happening. Any other question? Anyone else wants to ask any question?
Sir, could you go back to that cobalt graph? That there was one. Yeah, sir. In that cobalt HCP, sir, you were saying something regarding the fact that that parallel C axis goes easily into the saturation region.
Yes.
And
yes.
C perpendicular C axis takes a lot of time. Means a lot of
external
not
field.
time, external field. Yeah,
Yes.
yeah.
Yes.
So could you talk why? Could you say again why I Didn't follow
Why?
that part.
Okay, see, of course, I never argued out why even for a BCC. What I'm saying is that is determined by the crystal structure. Okay, so there are certain crystal. I mean, there is a coupling between the crystallographic orientation and the spin orientation. What kind of a coupling? I am not going into the details. I will, if you are interested, I will give you a reference, or we will work it out in the next course. Because I have to do the calculations. You understand? All these things are born out of the calculation, but I am showing you now as an experimental result. See, if you take, without even doing any calculation, you take iron. If you have a single crystal of iron, and you know that this is a 100, this is 110, this is 111, and you go and do a magnetization, you will get this curve. So that is what I am explaining. I am saying that, okay, this is the easy axis, this is the intermediate axis, this is the hard axis. Similarly for cobalt, this is the easy axis, this is the hard axis. Why is a good question, but then for that I need to do the calculations, and I will do it in the next course. No, otherwise, no, what happens is this 14 weeks will go for doing the calculations of magnetism. My point is, by next week I want to stop this and then go to the demonstration. I want to demonstrate BH loop, then talk about superconductivity, demonstrate that. So, okay, so there is a plan. I want to give you some flavor of experimental signatures, which determines and which tells you that why we have domains and what actually, why domains are important and all. Okay. Yeah. So any other question on this view graph? Anyone else is there? I want to check again whether students are there or they left. 41 are there. Yes. So people can ask questions. Okay. I will only ask the question. See, I am marking this as with a line. What does it mean? How can you have suddenly a switch from this to this? What happens in this kind of a situation? Anyone know? Do you know what is this called? What is this called? This region? This is a domain. This is another domain. And the region which separates two domains is called domain wall.
Domain walls.
Yes. You have heard about these things, isn't it?
Yes, sir.
Yeah. So domain wall is very, very important. Okay. Domain wall is very, very important. And then the question, another question is, why did you stop at 4? Why can't you have 8? Why can't you have 16? And is there any number? I mean, how long can I, how much I can go on dividing before I hit upon something? So these questions are important. So we will address that. So what is a domain wall? That is something. So what happens in a domain wall? What do you think will happen in a domain wall?
Sir, the spins, the dipoles which are near the domain walls, there will be an effective magnetization, I think, means towards the direction.
Okay,
means,
so we'll try to see. Okay, I'll read this slide before we, okay, we will come back to that. See, this I already explained, except to this magnetoelastic energy. I will discuss that later because people will get confused. In yesterday's class, I introduced this. In previous class, I introduced this. In today's class, I introduced this in terms of demagnetizing energy. So what I'm going to do now is, I'm going to see, this is like, one domain, the blue one, and the red one is another domain. And in between what I am showing here, this is not a single line. This is actually a domain wall. It has a specific orientation. That means from this orientation to this orientation, this 180 degrees is actually spread over a number of spins. It's not just, suddenly you have a switch. Why? Why? Because I'll give you an exercise now. You consider 3 spins. Okay, can you actually, I do not know how many of you have paper and pen with you. Do you have? If you have, please mark 3 spins with spin parallel. All the spins are parallel, and let us say on each spin there is a magnetic moment associated with given by S. So each one of them has a magnetic moment S on each one of them, and so initially they are all parallel. So what is the energy associated with this 3 spin system? I'm just assuming 3 spins. Okay, so what should I do? I'll say that, okay, two spins are coupled through exchange interaction, and the energy is given by minus 2j Si dot Sj. So that would be minus 2j, and Si is equal to S, because I told you that it on all the sides I, j, k, the spin is S only. Okay, so S, and in another spin J site also there is a spin S, and both are parallel, so the angle between them is 0, so they have a maximum component of S, so that energy is minus 2j S square. Is that okay? Did you follow? So what did I do? I took 3 spins, and then I am demanding that all the 3 fellows are parallel, and I am calculating what is the energy associated, exchange energy associated with this configuration, because I know the Hamiltonian. Hamiltonian tells that minus 2j Si dot Sj. Si dot Sj mane is the spins at neighboring sides. So when I say I, j, k, so I and j are parallel, so all the 3 have the same spin S. So S into S would be S square minus 2j S square, and these 2 fellows, again same thing, minus 2j S square. I am neglecting the, because I am considering only the nearest neighbor interaction. So the total energy associated with this 3 spin system is minus 4j S square. Did you arrive at this? How many of you arrived at this?
Yes, sir.
Right. Okay, now I'll give a question. I'll say that in this configuration, the second fellow, I am putting anti-parallel to the other 2. Okay, so still it's a 3 spin configuration, but the 1 spin I am putting anti-parallel. So what is the energy associated with this now? Can you please tell me? With this configuration?
0.
Who said that?
Sudama.
Huh?
Sudama.
I can't hear your name again. What is the name? Admit, someone is entering now. Okay. Who is that? Who said 0?
Sudaman.
Sudaman, why is it 0?
Because one it is 2j square, for another one it is minus 2j.
Arey Baba. See, I am putting the middle one anti-parallel to the other 2. So what should I do? I will consider 1 and 2, which are anti-parallel. Okay. So the energy associated with that would be plus 2j S square. Isn't it? Because j is given, I'm not changing. So because these 2 are anti-parallel, the cost 180 is minus 1. So the energy associated with that would be plus 2j S square. And say 2 and 3 are also anti-parallel. So what is the energy associated with that?
2j.
Plus 2j S square again. So what would be the total energy of this system?
Plus 4j.
So if I flip one spin, then what is the change in energy? From the ground state. Ground state mane when all the 3 are parallel. Okay. When because of excitation, because of temperature, let us say that I flipped one spin. Because of that, the excited energy is 4j S square. So what is the change in energy?
8j.
8j S square. And you know, j is generally very large. So 8j S square is a very, very large energy. So that means if I have to flip one spin, I need to spend a lot of energy. This is not practical. Okay, this cannot happen. But then when I increase the temperature, I know that the magnetization has to decrease. That means the spin has to flip. Otherwise, how do I get there is a decrease in magnetization? So what happens is the spin will not flip at a particular side, but it will prefers to this flip. Flip when I say from theta is equal to 0, it has to go to theta is equal to pi. Okay, so this pi angle, if it can be spread by a number of spins that are there in the system. Okay, suppose there are n spins. If this flip of pi angle is shared by n spins, then the energy associated with that will be much lower. Okay, I will actually continue this discussion in the next class, but please remember, I mean, try to, I will actually share Kittle's 2-page document, I mean, thing also. This is very, very important for another experiment. Okay, so this sharing of the spin reversal or spin flip by over a number of spins is called spin wave. It basically constitutes a wave. Like you have from 0, it goes to pi over shared by a number of spins. So this excitation is called spin waves. Okay, for our nickel resistivity experiment, this is very, very important. That's why I'm introducing here. So I'll go back to my configuration. But you see that I cannot flip like a line. I just to draw I'm drawing a line here, but this line is actually not a sharp boundary between these two fellows. I take a microscope and a magnifying glass and look at it. It is actually very wide. And in this wide region, there are number of spins which are there over which this spin reversal is taking place. Okay, so to reduce the energy associated, and the energy that is involved in reversing this is actually that is the energy associated with creating one boundary wall. So the moment you create a domain wall, you are spending some energy so that this reversal takes place. But then the energy that you spent, if it is less than the decrease in the magnetostatic energy, the system prefers to break into domain. But if you spend more energy in breaking the domains than that you gain in reducing the magnetostatic energy, then the system doesn't break into domains. So that puts the limit on the number of domains or the size of the domain. Okay, so this is some involved argument. I would encourage all of you to listen to this. I will stop it here for today. So we will discuss.
Sir, as you said that
I'll take questions once I stop recording. I'll take questions. So then we can discuss.